Good day and welcome back to part 2 of our discussion on exponential growth and decay. In this video, we will focus in on a specific physical property known as Newton's law of cooling. I will, whenever possible, abbreviate this as NLC, and you are certainly more than welcome to do the same. Similar to our previous discussion, what I would like to do is start off with the following description of Newton's law of cooling in words and transform this into a more symbolic or mathematical equation and see if we can use our previous knowledge or discussion to come up with a solution. The rate of cooling or heating of an object is proportional to the difference in the temperature between the object and the surrounding medium. So what I'm always picturing in my head is some physical phenomena that we can visualize. For example, you pull a can of soda out of the refrigerator and you sit it on the counter. That can of soda is going to slowly warm up and approach that ambient room temperature. So let's see if we can figure out a way to model this. And as a typical starting point, we need some notation to work with. And I'm noting two quantities to represent. There's the temperature of the object. So I'm going to let big T of little t, and I know this notation is not the best, but it's the standard or conventional notation we'll find in almost any book. So I'm going to go along with it. So big T of little t represents the temperature of that object, so our can of soda, at time t. So big T is the temperature of the object, little t is representing time. Then we also have this kind of surrounding medium temperature. So I'm going to let T sub s be a constant that represents the surrounding temperature. So that is a quantity that is fixed and will not change throughout the problem. Now let's focus in on a few key phrases. The rate of cooling of an object. So the rate of cooling or heating is describing a derivative. If big T represents the temperature, its derivative would be the rate of cooling or heating, i.e. a rate of change. So that gives us d big T, d little t. We are also told that this is proportional, so that means equal up to a constant multiple of something. So the K is because we have two proportional quantities. And what it's proportional to is the difference in the temperature between the object and the surrounding medium. So difference means we're subtracting, and it's a difference between the temperature of the object and the surrounding medium. This is the equation that we typically think of as relating to Newton's law of cooling. What we would like to do is see if we can maybe come up with a solution to this. And note, this isn't something I'm going to ask you to recreate, but instead when we have the solution, it's just something we can use. But it utilizes a nice kind of technique. What I want to do is just make an observation. If I let y of t represent T of little t minus T sub s. So T sub s is a constant. Big T of little t is a function that depends upon t. If we differentiate both sides, we would have dy dt is d big T d little t. So if we combine this together, the d big T d little t on the left can be written as dy dt. And on the right, we have k times t minus t sub s. T minus t sub s is simply y of t. So by using this, what I will call a substitution, we've rewritten this differential equation in a more familiar form. This is what we were looking at in our previous video. We know the solution. y of t is equal to y of 0 e to the k t. And let's just put this in terms of our function y of t to the left, i.e. with integration you might be thinking of a resubstitution. So y of t is t of big T minus ts, and y of 0, if you substitute in little t is 0, gives us the following. So the temperature of the object at any time, if we isolate it, is the surrounding temperature plus this quantity above. And what I would like to emphasize here is there's nothing that you need to memorize, but instead I'll note that if we encounter, say, Newton's law of cooling on an upcoming homework assignment, you would be able to use this circled formula directly. What is a nice exercise is making sure that you understand taking this statement in words and converting it into the mathematical or symbolic representation. Let's look at a kind of standard example now. A turkey is taken from an oven when its temperature is 185 degrees. So it's going to be some initial type of data, and placed in a room whose temperature is 75 degrees. So intuitively, the temperature of that turkey is going to be slowly decreasing and somehow approaching that ambient temperature. What we would like to do is find a formula representing the temperature of the turkey after t minutes if it has cooled to 150 degrees after half an hour. So let's indicate a few key bits of information. 75 degrees represents the surrounding temperature. The 185 degrees, that represents what we might think of as the temperature of the turkey at time 0. So time 0 is when we remove it from the oven. And it is 150 degrees after half an hour. We do have to be somewhat careful with our units. We're asked to find the temperature of the turkey after t minutes, so half an hour would refer to 30 minutes. So we have the following scenario. This is most definitely one of our Newton's law of cooling problems. So we can represent it in this form that we have above. The temperature of the turkey decreases at a rate proportional to the temperature of the turkey minus that surrounding temperature. We have the initial data that T of 0 is 185 and T of 30 is equal to 150. And I'll note we really need both of these pieces of information. One of them is going to be directly involved in the solution. The other is going to be necessary to solve for this kind of constant of proportionality K. And I would now like you to pause the video, give yourself maybe 5 to 7 minutes, and solve for T, the temperature of the turkey after T minutes. Now that you've paused the video and you've thought about this, let's go ahead and summarize. We can immediately jump to this formula that we've determined above. There's no reason to recreate the wheel. We just go to this generic form. Our T sub s is 75 and T of 0 is 185. So from above, we can immediately jump to the representation that the temperature of the turkey after T minutes is the surrounding temperature, 75, plus the initial temperature minus the surrounding temperature, e to the k t. That is, T is 75 plus 110 e to the kt. And just like we did in one of our previous examples, we need to solve for k. And we use this secondary data. We get back a temperature of 150 when we replace T with 30. And in order to solve for k, we need to isolate the exponential and use properties of natural logs. So we will subtract 75 from both sides to leave a 75 on the left, and divide by 110 so that on the right we simply have e to the k times 30. So to get to that k value, we need natural logs. So note the natural log of 75 over 110 is equal to the natural log of e to the k times 30. And note in this case now the e and the natural log cancel, and we're left with simply 30 times k. So if we want a formula for k, we have the natural log of 75 over 110 on the left, and we divide by 30. And that should do it for us. If we take this number and substitute it back in for k, we have the following formula representing the temperature of the turkey after t minutes. 75 plus 110 e raised to the kt. So k is the natural log of 75 over 110, all divided by 30. And this number is being multiplied by t. I do want to make one small observation here, more or less kind of just for fun and to make sure that this is matching up with our intuition. Since the temperature of the turkey is decreasing, we should have some type of exponential decay, which means that our constant k should be negative. So is it clear that k is really negative? And I'm going to say with a little bit of analyzing, we should be able to convince ourselves that that is true. So the first thing I'm going to do is just remind you what the graph of the natural log looks like. The graph of the natural log has this form, and its x-intercept is 1. What I want to observe is 75 over 110 is less than 1. And what that implies is that the natural log of 75 over 110 is going to be a negative quantity. So if we have roughly 75 over 110, the natural log of 75 over 110 gives you a negative output. And if that's negative, and you divide by 30, k will be negative as well. And this completes our discussion on exponential growth and decay, kind of just a detour to explore some properties of exponential functions, natural logs, and foreshadow a bit for those of you who will go on to take differential equations. Make sure to look through suggested problems in the book. Let me know when you have questions. Do not hold off on asking your questions. Stay tuned. Take care.